Welcome. My name is Mario Drobics. I'm the head of the Competence Unit Cooperative Digital Technologies at AIT. In the next 30 minutes, I will give you an overview about the results we have achieved in the national flagship project IoT4CPS. I will start with a short motivation to recap the initial goals of our project. Currently, we are facing an increasing cost and time pressure in all industrial domains. To address this, we need to reduce the time of market by providing security design patterns, tool and reusable components along the whole value chain. Secondly, we see an increasing usage of data. Data is used everywhere. It is used for predictive maintenance. It is used to create new services and businesses. Here we need to support the increasing connectivity that is caused by this demand on data. This goes down to the IoT level so that we connect all sensors, that we connect the products, but also to the shop floor in the production sites. This connectivity needs to be addressed in a secure and reliant way in order to provide a solid and resilient foundation for data collection. A special attention has to be paid to wireless connectivity, specifically in the domain where safety issues are important. Finally, by creating these new connected and data-driven products and services, we need to ensure security along the whole life cycle. It is no longer sufficient to only define security measures at the design phase, but rather we must define and reanalyze security and potential threats during the whole operational phase of the products as well. In our project IoT4CPS, we aim to provide tools, methods, and guidelines to support companies in this digitalization process and to improve and decrease the time to market needed for developing such connected products. In our project, we have specifically focused on two use cases. One, the product-oriented use case, is the connected car. Connected cars are now a big topic. With the increasing autonomy level that is aimed for in these cars, we need a lot of sensor data in the car, but also data that is shared with the environment. On the other hand side, we have the production sites, where also connectivity is getting increasingly important, where flexibility becomes a major issue, and where especially wireless connectivity can bring large efficiency improvements over time. In our project, we have analyzed the needs of the industry, developed methods and tools to support the development and operation of such connected services and products, and then also created demonstrators that showcase how this can be utilized for concrete industrial applications. To do so and to address this topic of safety and security in such a broad and deep way, we combined the capabilities of leading industrial and research organizations. We have overall had 16 partners in our project, ranging from large industrial companies like Infineon, TTTech, NXP, but also Siemens and Nokia, to the scientific partners that were gathered from all over Austria. Scientific partners have been the TU Vienna, the Technical University of Graz, SBA Research, TU Graz, Johannes Research, Salzburg Research, the Software Competence Center in Hagenberg, and the University in Linz. The whole consortium was managed by AIT, the Austrian Institute of Technology. The overall budget of the project was above 5 million euros, where we received roughly 3 million of funding from the ministry and the FFG. The runtime of the project was 3 years, so we started in December of 2017, and we are now having our final months of the project, and thus we are now presenting the outcomes of our 3-year research. As already mentioned, the approach of the project was to start with the needs of the industry. So we went down and analyzed the use case objectives in these two domains, the connected car and the connected factory. And from this use case objectives, we defined the actual research goals that were addressed during the project. The research goals were separated in 3 domains. On the first hand side, we had the design phase. So we looked here into methods how to design safe and secure systems from the beginning. How can we ensure that security is embedded already in the design, in the architecture of these components and systems. Secondly, we addressed the issue of operating and maintaining security over the life cycle of a product by verification and analysis of potential threats and the behavior of the system. And finally, we addressed also the issue of IoT lifecycle management. How can we gather data in a secure and trustworthy way over the lifecycle of the product? How can we store this data? And also how can we utilize this data to analyze security threats, to manage security proactively over the lifecycle of the product? Finally, these different developments have been put together into industrial demonstrators, 1 demonstrator in the connected car environment and 2 demonstrators in the connected factory. These demonstrators aim to showcase for other companies how these results can be incorporated into an industrial environment and what benefits they can bring, and that they are already ready to use in industrial environments as well. By creating this large set of results that have been created during the project, we really aim to provide the foundation for Austrian industry to increase the product quality, to develop new services in a trustworthy way, to reduce the time to market, to increase the efficiency, and also to increase productivity in the development and the maintenance of connected products. So, what concrete achievements have we made in the project? As already mentioned, the topic of security and safety is quite a big topic and needs to be addressed from different perspectives. In our project, we have structured the technological development along 2 main dimensions. On the one hand side, we have the product lifecycle. So we start, as already mentioned before, with the design of according components. We then look into the verification during runtime, during operation, and also address the whole lifecycle management of these products, the security requirements, and the data over time. On the other dimension, we need to look at the integration level. We start from the physical level, looking into hardware requirements, hardware properties, and hardware or hardware-based methods to ensure security and trustworthiness, but then also move up to the network level. We have researched how secure connectivity can be achieved, also with low-powered devices like in IoT environments, and in flexible environments like the connected car, where we have changing environments, where we have changing players involved. But then also look at the platform level. How can we ensure, for example, security in a connected car where we have dozens of components being integrated from different vendors? And then, of course, we also need to look at the application level. How does the whole set of components work together? How do they ensure trust between each other, even if we have, for example, distributed production facilities? The human level is very important. On the first hand side, we need to support humans in designing and developing secure solutions by providing them ready-to-use patterns, architectures, methods, but then also to support them in carry out extensive testing according to the requirements that have been defined. On the other hand side, we need to analyze what behavior, what manipulated behavior a human might make to the system. By social engineering, for example, a lot of IT attacks are carried out. So we need to also consider the human vector when designing safe and secure applications. Now, let's have a deeper look into the technical innovations that have been developed within IoT4CPS. We will start with the design methods, so with the design phase of secure components, And there we can already see a strong shift towards safe and secure co-design. This is caused by the fact that when we go to the cyber-physical world, we see a combination of cyber threats and physical threats. This has to be already considered at the design phase, because often these requirements are from different perspectives, have different implications, and by addressing them already early in the design phase, we can find an optimum solution that considers both aspects. Secondly, as already mentioned, we have an increasing time and cost pressure, so there is a high demand for ready-to-use solutions that not only increase the efficiency, but also the effectiveness, as they have already been tested and proven to be secure. And finally, especially in this context of constrained devices and time constrained devices like Internet of Things applications, we need to specifically consider how we can implement crypto algorithms in a secure way also in these restricted devices. So the design also considers all different levels of system development. So at the application level, the goal is really to identify security threats already in the design phase and adapt the design and architecture of the solution accordingly. At the platform level, we are looking at self-healing structural adaptation, so how we can prevent a failure to cause a further error of the system. On the network level, we have developed a recommender system that provides recommendations for system engineers which protocol to choose best according to their requirements. And on the physical level, we have developed a cryptographic library that provides support in rolling out cryptographic secure solutions to IoT devices as well. So when we look at the design on the application level, it is important to get an overview and to identify potential threats to a system in a structured way. We are supporting this project with a tool that we have developed within IoT4CPS Threatget that enables the system designer to configure his system or her system in a flexible way by using predefined components. For these components, an associated threat list is already available with according mitigation measures attached that enables the designer to analyze potential threats even in a complex setting quite easily by relying on the existing threat definitions, and also by having the links to the according standards and requirements for using certain components. This dramatically reduces the development time and increases the trustworthiness of the developed solutions. By using these threat models and threat lists, it is also possible to automatically carry out functional and formal checks. These automatic checks can be done by creating, for example, a catalog for the pen testing, or by creating test cases and executing them automatically based on the threat list. This is also very important when the system is maintained over time, because when the requirements are changed, maybe in a later iteration of the product, then also the according threat database is updated and the tests are automatically updated too. This ensures that all the requirements that have been defined are automatically considered also in the testing, and that any potential side effects of changes to the system are identified easily. When we look at the platform level, it is important to ensure the secure operation of the system also in the case of a failure. This can be achieved by applying self-healing by structural adaptation. This means that the system automatically rearranges its components in a way that the core functionality is still provided and that the safety of the passenger, for example, in the car, but also the environment is still ensured. The structural adaptation can be carried out in different ways. So for example, if a sensor fails, it can be replaced by a different sensor that provides the same functionality. Take for example a LiDAR sensor. If the LiDAR sensor fails for a limited amount of time in a restricted setting, maybe also an optical sensor could take over the functionality. Then we are talking about replacing of failing components. But in the case of the communication network, when we have a communication error occurring, it might be necessary also to reconfigure the information flow. In any case, it is important that substitutes do not alter the system so that we have a freedom of interference from the mitigation measures. It is also important to contain faults in order to avoid propagation and to ensure information access. This information access is especially important for analyzing the causes of an error, but then also for the continuous monitoring of the system and in order to find a suitable substitution for the problem occurring. In IoT4CPS, we are supporting self-healing by structural adaptation by two measures. On the one hand side, we are providing architectural patterns to enable that and to design the system in a way that structural adaptation can be achieved. And on the other hand side, we are also providing according runtime functionality that can be implemented to enable real-time adaptation measures. When we look at the network level, we have seen that there is often a challenge to find the most appropriate communication protocol and architecture for a certain application. In IoT4CPS, we have developed a recommender system that can compute a feasible system setup based on the requirements specified and also suggest a according system topology. This simplifies the design of complex communication applications and also increases the trustworthiness of the overall system, as it can be ensured that the requirements that have been specified can be met with the chosen communication protocol and architecture. Finally, to address security also on the physical level, we have developed methods which enable the usage of secure cryptographic methods also on restricted devices, which usually create a lot of overhead and reduce the efficiency at the device level, but also on the communication protocol. We do that in two directions. On the one hand side, we provide efficient and low latency forward secure state-of-the-art key exchange protocols. And on the other hand side, we have developed efficient and practical side channel resistant authenticated encryption schemes on constrained devices. These methods are available for system designers, developers, and they can utilize that to also increase the level of security in their restricted devices. So considering security during the design phase is very important. But we also need to monitor our security properties during the operation of the components of the system as security environments and demands change, as the environment where the system is used can also change and new threats can occur over time. We are addressing the issue of online countermeasures that are required to ensure security during the operation and also to provide scalable testing methods to validate the system properties even during the operational phase. Again, we are looking in this verification and analysis on different levels. On the human level, the application level, but then also, of course, the network communication level and the hardware physical level as well. When we are talking about human aspects, we are talking about the design phase, where we have to support designers in designing secure applications by providing them according guidance and documentation, but also preventing typical errors in the implementation early on. And secondly, of course, we are also talking about errors that can happen during the operation, intentional or unintentional, and this is addressed with IoT4CPS. Within the project, we have focused on automated model checking of human aspects to verify human errors in a formal manner and to carry out symbolic model checking. This has been implemented in an extension to the Tamarin framework that can then be used to model human errors when interacting with these components. For the application level, within IoT4CPS, we have developed the Analytical Toolbox. This is a collection of tools for different system levels that analyzes the normal behavior of the system and identifies any deviations from the normal behavior to raise an alarm, to initiate mitigation measures. The levels that we are looking on are on the network level, the information flow. So who are the recipients of the information, at what frequency, what amount of data is usually transferred. This all can be analyzed, and any deviation might give a hint of a potential attack to the system. But we are also looking on the system level in the log files to identify any deviations in the operation of the system. But then we also have a look at the hardware level, where we monitor certain hardware properties like the temperature, the energy consumption, and so on, to detect any activities that might deviate from their intended behavior. Within IoT4CPS, we have developed a whole architecture that consists of different components and that can be easily reused also in other applications or scenarios. So if you're interested, feel free to have a look at our website where you can find more resources on that. At the network level, we have specifically looked into the connected car case, where the usage of Ethernet is becoming increasingly important as the vehicular network bus. Within the project, we have defined an experimental version of the Internet Protection Profile, and within IoT4CPS, we have developed a prototype for an Ethernet protection profile, which consists of multiple components. The main component is the TOE, the target of evaluation, which consists of a deterministic Ethernet switch and CAN gateways that is completely located within the car and that covers multiple communication standards to collect all the information that is security relevant and gives information about the behavior of the network in the car. We have also outlined potential security problems and objectives in order to give guidance to system developers, and we have defined security functional requirements and evaluation assurance levels in order to provide further guidance for the development of a vehicular network bus based on Ethernet protocol. So finally, on the physical level, we are also providing different tools to protect the hardware from manipulation and also from the extraction of information. So a central element is to ensure that random numbers that are generated to create cryptographic keys are secure and are not manipulated and cannot be analyzed. And to do that, we have developed a dynamically exchangeable runtime checker in hardware, which consists of different hardware apps that monitor the behavior of the random number generator. Furthermore, we have developed a formal verified side channel protected hardware, which provides measures to counteract the power analysis of hardware components by masking the intermediate results of, for example, a cryptographic algorithm. And finally, we have developed formal hardware property checks, which enable the detection of hardware-based Trojans, and this is done using statistical traffic modeling. So we have covered the design phase, we have covered the operational phase, and in the third pillar, we are looking at the IoT lifecycle management. The IoT lifecycle management becomes increasingly important, especially when we think about digital twins, where a lot of data is gathered from the products being in use to create a simulation model for further analysis, for improvements of the product. And of course, this digital twin can also be used for security analysis, monitoring, in order to increase security over the whole life cycle of the project, of the product. Within IoT4CPS, we have been looking at the life cycle of the connected car. We have created a framework for collecting data from different cars and other sensors, and applied it to different usage scenarios. The data is fed into a digital twin stack where all the data can be visualized, can be analyzed, and we have specifically looked into ways how to utilize this data to identify security threats, to monitor security issues, but also to provide a secure configuration management of the connected car over time. So these have been the technical developments, and there are quite a broad range of them, and on very different aspects of the development, operation, and maintenance of these cyber-physical products. In order to bring these developments to use, however, it is important also to implement them in concrete applications in the industrial setting. And this was the aim of our two demonstrators. One in the autonomous driving context, where we have created a connected driving demonstrator that collects data from a car and transfers this to a backend system where it can be used for system analysis, for monitoring, for carrying out tests with the car. In order to establish this secure data communication with the car, we are using the secure communication network in the car, have established an according connectivity to a backend solution, and that involves also a remote control via the smartphone, which you can see in the left-hand corner, where it is possible to securely control the car just via the smartphone. Of course, this is just a demonstrator, but the intention here is really to provide a cognitive open vehicle platform where relevant vehicle data can be securely collected, where we can utilize this data to analyze the development, the behavior of the system to support testing of cars in the field, but then also further on to utilize this data for creating a digital twin model of the car itself. This requires, of course, the secure and reliable communication of the car with the environment, and this is something that will become increasingly important when we think about the possibilities 5G is opening up. We have also investigated and utilized methods developed in IoT4CPS for enhancing the security of the driving platform of the network in the car, and we have also carried out an extensive threat analysis of the automated driving platform at the beginning in order to expand the threat catalog and the list of possible mitigation measures for this automated driving use case. The second demonstrators are situated in the context of the smart production environment, and there our aim was to showcase the high degree of reusability that the components we have developed has, so that it can be easily deployed to different industrial settings, to different production sites, and that can then lead to an increase in efficiency in setting up and maintaining these industrial processes. This is achieved by providing trustworthy connectivity and especially wireless connectivity also at the production site. And we're providing here guidance and want to inspire people of using these digitalized solutions also in their production environment. Concretely, we have developed two demonstrators. The first demonstrator is mainly addressing the aspect of collecting data from remote devices, from remote production sites. So the focus here was really on the secure connectivity across different layers, integrating that data, creating a digital twin model in order to optimize the production processes, to increase automatization, carry out predictive maintenance, whatever data-driven applications you can think of. The second demonstrator was focusing on the case of legacy production sites where you might already have a certain degree of connectivity, but not having that high level of security being set up in order to connect this factory to the internet. And there we have utilized a security by isolation concept that enables the protection of legacy environments by using a secure gateway, which then provides the functionality for data exchange, for remote access, also for these legacy environments. And this is something that is very important, especially in the industrial setting where we have decades of operation in these environments. So these have been the developments of the project so far. And of course, when you're interested in accessing this broad knowledge and know-how and want to learn more about, we are providing different means of information. So on the one hand side, we have created 6 white papers that address the different aspects I have just talked about in a more in-depth manner. They are very comprehensive in terms of coverage and to provide also a good overview on the different topics. Of course, if you want to go deeper into the details, we are providing different publications on the scientific level, but then also the public deliverables that can be downloaded from our website. And of course, we also have the technical results where we have certain open source projects, we have some prototypes, we have conceptual papers that all can be found on our website. If you're interested in more details, then of course you can always also contact us as a project, and we will be happy to provide you a link to the corresponding partners that have contributed and developed the specific components. If you are interested in seeing the demonstrators in action, then please contact our industrial partners. We have them installed at the industrial sites, so they are not publicly available, but nevertheless, we have documented them, and so you can use them as a reference on thinking about how to implement the technical achievements also in your environment. As already mentioned, all this information can be found at our website, IoT4CPS.at. That's it from my side. I hope you have now a better overview on what we have achieved. You have got some inspiration where you could utilize the different components that we have developed also in your environment, maybe also of new services, new products that could be enabled by using these trustworthy components. I'm happy to answer the questions now, and thank you very much from my side. Thanks a lot to my colleagues who have put in a lot of effort in carrying out this project, and to all the partners for this successful 3-year journey. Thank you very much. Bye-bye.